Dear colleague, I'm Claire Vigneault from France, and first I would like to thank you to let me present our work entitled Bisphenol S, Impaired Estradiol Secretion During Ovine Basal Folliculogenesis in Vitro. Our study follows an alarm raised in 2013 by the WHO and the United Nations Environment Programme on the multiple adverse effects of endocrine disruptor, and more specifically on the impacts on reproduction. In our team, we are particularly interested in bisphenols. We all know now that they're ubiquitous. So for example, they are on receipt tickets, food containers, or medical consumables, and even recently published in embryo culture media. A French report in 2011 attesting several bisphenol A effects on health and especially on reproductive organs and reproductive function lead to gradually forbidden from food containers to the receipt tickets lately. Thus now worldwide interdiction has led to structural analogs emergence as the BPS, and this one is known to be more stable, more resistant to heat and sun, and therefore less biodegradable. Multiple studies have highlighted the BP in multiple human biological fluids, and more recently in follicular fluids, as BPA and BPS. It is important to note that the values are large because they can vary widely by socio-professional category. So what are the effects of BPS on ovary? Some results show an estrogenomimetic effect and anti-androgenic effect, decreasing oocyte maturation and disrupting hormonal secretions, specifically on estradiol and progesterone. Indeed, according to a recent study did in our team, we can see that progesterone decrease and estradiol secretion increase after 10 micromolar concentration of BPS when you expose granulosa cells after 48 hours of treatment. You can note that no effect has been shown on viability. Overall, all the effects I described above are found during terminal folliculogenesis. To my knowledge, only a few studies are shown a decrease in the number of primary and preantral follicles, and this is mainly in the mouse model, so not in monoovulent model. Given this lack of knowledge of the effects of BPS on basal folliculogenesis in monoovulatory species, we decided to study the effects of BPS at different concentrations in an ovine in vitro follicular culture model with a particular focus on the preantral to antral transition. To do so, we evaluated 3 criteria: the follicular survival, the basal follicular growth according to the evolution of the diameter and the appearance of the antrum, and finally, the follicular hormone secretion. To do this, we use the following methods. From EU lamb ovaries, we extracted follicles between 180 and 240 micrometer without antrum. This follicle was then divided in, I would like to show you, in 3 conditions. And then, in 3 conditions, the control BPS 0.1 and BPS 10 micromolar. Then they were placed in an oven at 38.5 Celsius degrees and 5% of CO2. At day 6 and day 13 and day 15, We assessed survival according to follicular integrity, oocyte clarity, and the evolutions of follicular size, but also individual diameter and interim appearance were assessed. The cultural media were frozen at day 13 and day 15 for subsequent hormone assays. The follicles were individually frozen at day 15. In the end, 7 batches were kept. As a result, we can see that there is no significant effect of BPS on survival rates. We can also say that in our study, there is no significant effect of BPS on the evolutions of follicular diameter and on the follicular interim appearance. So globally, no effect on follicular basal growth. But according to the estradiol secretion, we can see a major effect of BPS on it. Indeed, when we compare the estradiol secretion of the follicle exposed to the control, we can see a decrease of 49% in estradiol secretion at a concentration of BPS 0.1, and so the less concentrated, and a decrease of 9% at a concentration of BPS 10 macromolar. However, we did not see a significant effect on progesterone and AMH secretion. So in conclusion, we can say that BPS causes disruption of steroidogenesis during basal folliculogenesis without impairing survival and follicular growth in vitro, and specifically after a long-term exposure. That fact underlines the necessity to assess the risk of BPS exposure for reproduction of monoovulatory mammals as human. And we think that our study gives a new argument to consider BPS as an endocrine disruptor. In the future, we will study different gene expressions on wool follicles. So we have about 40 follicles per condition, individually frozen in lysis buffer. And we have selected 20 genes that will allow us to study enzymes of steroidogenesis conversions, molecules involved in follicle functionality, and enzymes involved in oxidative stress mechanisms of these follicles. So thank you for your attention, and I would like to thank the Bingo team who support my work and give me the opportunity to study this really interesting research topic. Thank you.
Ladies and gentlemen, dear Chairman, today I'm pleased to present you a part of my thesis entitled Effect of Ceficocinin Verified from Spirulina platensis on Preserved RAM semen quality and fertility rate. First of all, let me please introduce this topic. I will start by an introduction, objective, materials and methods, results and discussion, and finally, conclusion. Artificial insemination is an important technique in livestock sector. This technique is mainly based on semen storage in liquid or frozen form. In the field condition, liquid storage is more suitable for a successful pregnancy. However, handling semen can lead to irreversible damage at the cell level due to cold shock as well as to lipid peroxidation in the presence of reactive oxygen species. Accumulated free radicals can lead to oxidative damage to the spermatozoa reducing its motility and fertility. This underlines the importance of supplementing extenders with add antioxidants that would minimize the negative effect of reactive oxygen species and maintain sperm quality after liquid storage. The antioxidant that has been chosen in this study was cephalocyanin, which is highly soluble in water and has a high therapeutic value because of its antioxidant properties. Thus, the aim of this study was firstly to purify cephalocyanin from Spirulina platensis, and secondly, to evaluate its effect on the quality parameters and in vivo fertility rate of ram semen after liquid storage at 5 degrees. To achieve this goal, cephalocyanin was extracted using cold maceration in distilled water. The remaining cell debris was eliminated with ketosene and charcoal. Finally, extract was partially purified by aqueous two-phases system and finally purified by ion exchange chromatography. The in vitro antioxidant activity was evaluated using DPPH and AETE methods. To achieve the second goals, 50 samples were collected using artificial vagina from 4 adult fertile rams. Then semen was diluted to a final concentration of 0.8 billion spermatozoa per ml. In skim milk, without cephalocyanin as a control, while the tested samples included 1.2, 2.4, 3.6, and 4.8 microgram per ml of cephalocyanin. Semen was then stored at 5 degrees C. Several sperm parameters such as motility, viability, abnormality, and lipid peroxidation were recorded after 0, 4, 8, and 24 hours of storage. The 2.4 microgram per ml was chosen as concentration of cephalocyanin, leading to high-quality sperm. We decided then to use this concentration in artificial insemination trial. Concerning purification of cephalocyanin from Spirulina platensis, the table 1 shows that the purification process using aqueous two-phase system followed by a single chromatography step leads to high purity, which equal 4.06. The purity obtained by these methods is higher than those reported in other studies. The table 2 shows that at low concentration of cephalocyanin, it gave high free radical scavenging activity to DPPH and AETE. Regarding evaluation of the effect of purified cephalocyanin on the quality parameters and in vivo fertility rate, the two figures reveal that total and progressive motility decreased with storage time, while a significant improvement was recorded while cephalocyanin was added to the skim milk at a concentration of 2.4 microgram per ml. The same tendency was recorded while we studied viability. Regarding sperm abnormalities, we observed an increase related to storage time. However, cephalocyanin concentrations have no significant effect on abnormalities. Concerning lipid peroxidation, keep in mind that it increased with storage time. A significant improvement when cephalocyanin was added to the skim milk at a concentration of 2.4 microgram per ml. for artificial insemination trial, and based on heat detection, we recorded 80% of pregnancy rate, while the semen was extended with milk including 2.4 microgram per ml versus 60% in the control group. The beneficial effect of tifficocyanin is due to its antioxidant activity, which makes it a strong scavenger for reactive oxygen species and for protecting against oxidative stress. Same components of tifficocyanin, such as valine and same essential amino acids, have been reported to be involved in this process. To conclude, the tifficocyanin purified from Spirulina platensis show high in vitro antioxidant activity. 2.4 microgram per ml of tifficocyanin improved the quality of sperm during liquid storage and also increased the fertility rate. Thank you for your attention.
Good morning and good afternoon around the world. First, I want to thank the organizing committee for selecting our work for an oral presentation. It's an honor for me to present this study, Comparison of Sugars as Non-Permeating Cryoprotectant for Immature Equine Oocyte Vitrification. I would like to start showing this amazing picture from Jessica and Dalera. They just got the dressage golden medal in Tokyo. So can you imagine how much could cost a foal from Dalera? Well, let me tell you that it could be more than 20,000 euros easily, and that's why anyone might be interested in preserve her genetic. But how we do it? We do it by cryopreservation. We use vitrification. This is a cryopreservation technique which allows us to preserve cells over the time by applying very low sub-zero temperatures that stops cell metabolism. In the mare, to preserve her genetic, we can vitrify embryos or oocytes. Embryo vitrification is a successful clinical procedure, but to get an embryo you must have chosen the stallion and you have to make all the arrangements for the embryo production. Additionally, only half of the preserved genetic is female. That's why today we will focus on oocyte cryopreservation, the only way to truly preserve the female genetics. Unfortunately, so far results in equine immature oocyte vitrification has not been very effective. The best 4 studies show that vitrified oocytes reduce their developmental capacity more than twice when we compare to fresh oocytes. During vitrification, we have permeating cryoprotectants, which go into the cell replacing part of the water and preventing ice formation, and the non-permeating cryoprotectants, which are large molecules that do not penetrate the plants. They are normally present only in the final vitrification solution and the warming solution. They contribute to the viscosity of the solutions, helping to extract more water, allowing to lower the concentration of permeating CPAs. They also prevent a drastic osmotic shocks during warming. Meanwhile, the oocyte is recovering water and expelling the permeating cryoprotectants. But the question is, which one is better and how they can improve our results? In humans, in which vitrification is a clinical procedure, initially monosaccharides showed faster equilibration and better developmental competence in mouse zygotes. But later it was demonstrated that these saccharides has a greater influence on vitrification solutions because they can increase total solute at same osmolarity. Then, recently only the saccharide has been used with a better blastocyst quality and sometimes better blastocyst rate for trehalose over sucrose. In bovine, trehalose had better fertilization when 1 molar was used, but in porcine no difference were found in survival and developmental rates between sucrose and trehalose with 0.5 molar, so concentration might be important. But what happened in horses? Only one study compared sugars with further embryo development, and only a protocol using propylene glycol, ethylene glycol, trehalose was able to produce an embryo. So far, no study has compared sugars side by side with similar concentration, and a monosaccharide has never been tested in equine oocytes. That's why our main objective is to determine the effect of 3 sugars, sucrose, trehalose, and galactose, during vitrification and warming on the developmental competence of equine oocytes. To do so, in our materials and methods, we designed the following experiment. We collected mature oocytes from the slaughterhouse, and we partially removed cumulus cells. Then we divided them in 4 groups. 1 non-vitrified, which is the control, and 3 vitrification groups in which the protocol is the same. Only different sugars are used as non-permeating cryoprotectants: galactose, sucrose, and trehalose. After vitrification, these oocytes were warmed, and all groups of oocytes were moved to maturation medium at the same time. Then, 30 hours later, oocytes were denuded, and those with polar body were injected and followed up for cleavage and blastocyst formation from day 7 to day 10. I will briefly discuss the vitrification procedure in more detail. After collection, we keep the oocytes in base solution. We prepare droplets of equilibration and vitrification solution. Then, 5 to 6 oocytes are moved to equilibration solution, which has ethylene glycol plus diimiso, 10% each. They are there for around 25 seconds. Then oocytes are moved to vitrification solution, which has 40% of the total permeating CPA and 0.5 molar of the sugars. Oocytes are then loaded onto the vitrification device with a minimum volume and plunged into the liquid nitrogen. From vitrification solution to liquid nitrogen is around 40 seconds. After storage, oocytes are warmed by moving the device into the warming solutions for 5 minutes. The solution has 0.5 molar of one of the 3 sugars. After that, we move and wash the oocytes in base solution before transfer them to maturation medium. After this, we can move then to the results. Although galactose tends to result in a lower maturation rate compared to trehalose and control, there was no significant difference in maturation rate among groups. Cleavage was similar between treatments, but lower in sucrose group compared to the control, and it also tended to be lower than in the galactose group. Blastocyst rates for all vitrified groups were significantly lower compared to the control, but no significant difference were found between the 3 sugars, although galactose resulted in the highest numerical blastocyst rate with 7.6. If we look at the day that blastocyst appears, there is very similar between treatments, however later than control. In general, kinetics of development show that the blastocysts from fresh oocytes develop earlier, 8.5 days on average, compared with 9.3 days on average for blastocyst development from vitrified oocytes. And with this, we move to the discussion. We were very happy that we obtained blastocysts from all groups. However, blastocyst rates were still very low, so further optimization is needed. But for the first time, a monosaccharide like galactose was tested for equine oocyte vitrification, and interestingly, we obtained the highest blastocyst rate after vitrification. Based on the result, galactose should be considered as an alternative as non-permeating CPA for equine oocyte vitrification. When we evaluate the results, we think the difference between monosaccharides and disaccharides might be due to the amount of water displaced. So, different concentration in the sugars might be tested to evaluate this effect. Results also seems to demonstrate that a species-specific difference might apply, since triallose, the most used in humans, did not bring the best results in horses. And what is missing? What should be tested in the future? If galactose showed the best cleavage and blastocyst rate, but maturation tended to be lower, vitrification of metaphase 2 stage should be considered as an alternative. Or we could try triallose, which resulted in the best maturation for vitrification, and galactose for warming. On the other hand, sucrose resulted in the lowest cleavage and blastocyst rate, so perhaps sucrose toxicity might be considered in equine oocytes, as was demonstrated in dromedary camels. Finally, my take-home message is that with our short protocol, we were able to produce embryos from all groups, but efficiency is still very low for clinical applicancy. So further optimization is necessary, and galactose should be considered as a valuable non-permeating CPA for equine immature oocytes. This takes me to the end of my presentation. I would like to thank again the organization committee and all my colleagues, including those who are not in the pictures due to COVID. I'm glad now to take your questions.
Good afternoon. My name is Giselle Gamarra. First of all, I would like to thank AETE board member for the opportunity to present our work we realized in Oribe-Levache in France. The topic of my presentation is about a retrospective study of high bovine embryo production in ovum pica in vitro production commercial programs using heifer and cow donor oocyte and exsorted and unsorted sperm. According to International Embryo Transfer Society, in vitro production of embryo in cattle has shown significant progress in recent years. From 2016, the number of viable in vitro production embryo surpassed the number of transferable in vivo produced embryo. The OPU IVP technology combined with exsorted sperm is a promising alternative to produce more female embryos in a dairy cattle program. However, the use of sex sperm can result in variable blastocyst rate. The objective of this study was to evaluate the efficiency in IVP for exsorted sperm compared to unsorted semen on grade 1 OPU in vitro embryo production in high genetic merit hosting heifers and cows under commercial conditions performed at a biotechnology Oribe-Levache in Dengue, France. Oribe-Levache is a union of cooperative or artificial insemination in the south of France. We are in charge of system breeding program selection on which 14 in dairy and beef cattle and 2 in goat breeds. Our donor station and IVP laboratory are located in the southwest of France, in Dengue City. This retrospective study includes heifers and cow host and donor. With heifer donor, 145 in vitro embryo production sessions were performed with unsorted semen. This group is called G1, and 29 with exsorted semen. This group is called G2. With cow donor, 108 in vitro embryo production sessions were performed with unsorted semen. This group is called G3, and 334 with exsorted semen, called G4. One precision, IVF were done using different balls without any previous IVP testing. Before ovum pickup, heifers and cows were superstimulated with the following protocol. On day 0, donors received a progesterone device and follicles more of 8 millimeters were removed. Ovarian superstimulation starts on day 3 with decreasing doses of FSH, twice daily over 3 days. Total dose 350 micrograms for cows and 250 micrograms for heifers, with estimate for FSH. Ovum pickup was performed 12 to 24 hours after the last FSH injection. In this slide, you can see the in vitro embryo production process. After ovum pickup, cumulus oocyte complex were recovered, evaluated immediately, and placed in maturation medium for 24 hours with 5% CO2 at 38.5 degrees Celsius with maximum humidity. Cumulus oocyte complex were fertilized with frozen unsorted or exsorted sperm in modified tall IVF medium using different no-pre-testing balls. Resulting zygotes were cultured in soft medium up to day 7 at the same temperature with 5% CO2 and 5% oxygen with maximum humidity. Grade 1 expanded blastocysts according to International Hemotransfer Society classification were recorded on day 6.5 and 7. Now, let me present you our results. This graph shows in yellow bars the number of selected cumulus oocyte complex for in vitro maturation per session and the number of grade 1 expanded blastocyst rate per session in blue bar for heifers and in red bar for cows. No significant difference were detected in the total number of selected cumulus oocyte complex for IVN between groups. The number of grade 1 expanded blastocysts was higher in group 3, corresponding to unsorted semen with cow donor compared to group 1, 2, and 4. Here you can see that at day 7, grade 1 expanded blastocyst rate were not different between G1 and G2 group, and between G3 and G4 group. However, grade 1 embryo development rate was higher in cows compared to heifers. In addition, assuming a cell ratio of 50% in unsorted semen and 90% in exsorted semen, in cows, a high number of presumed female embryos was obtained in G4 group compared to G3 group. This significant difference has not been evidenced in heifers, maybe because the lower number the OPU IVP session in G2 compared to G1. In conclusion, our work confirmed the efficiency of OPU in vitro production technology to produce high number of grade 1 embryo using exsorted under conversion conditions. Furthermore, OPU IVP technology seems to be more efficient in donor cows than in donor heifers in terms of blastocyst rate. This last statement is confirmed in other publications. Thank you for your attention, and now I welcome your question.
Good afternoon, everyone. First of all, I would like to thank the AETE committee for giving me this opportunity to present here at this AETE Digital Webinar. I feel very honored to present to you my research focusing on the temporal changes in the oviduct following the introduction of an obesogenic diet in outbred mice with a focus on transcriptomic changes. A Western-style diet may lead to metabolic syndrome, and this is associated with many metabolic disorders. Such metabolic alterations may have a direct impact on oocyte and embryo quality and can thus lead to reduced fertility in women. The direct detrimental effects of metabolic alterations on oocyte quality have been documented. However, the impact on oviductal microenvironment, where fertilization and early embryo development take place, is less characterized. And furthermore, the onset and the duration of the changes after the start of a high-fat, high-sugar diet remain unclear. So therefore, the aims of this study are, first of all, to assess whether the introduction of a high-fat, high-sugar diet in a mouse model can lead to cellular and oxidative stress and inflammation in the oviductal epithelial cells at the transcriptomic level. And the second aim is to define the time frame during which these effects develop. So when do they start and are they permanent? To investigate this, we have the following experimental design. We use Swiss mice who are at the age of 7 weeks at the beginning of the experiment, and we use 3 mice per treatment per time point. The mice were separated into 2 groups, of which one group was fed with a control diet and the other group was fed with the high-fat, high-sugar diet. And this was done during 6 different periods of time. So there were 6 endpoints between 3 days and 16 weeks after the start of the diet. Here you can see a timeline to make this more clear. So at this point, we start the diet and we feed the mice the control or the high-fat, high-sugar diet for 3 days, 1 week, 4 weeks, 8 weeks, 12 weeks, or 16 weeks. During the whole experiment, the weight of the mice was monitored weekly. And since no significant aging effects were detected, and also based on preliminary comparisons between the high-fat, high-sugar mice and the control mice, and the patterns of the gene expression, we decided to merge the data into 4 biologically relevant phases. So the 3 days becomes the acute phase, the 1 week becomes the early phase, 4 weeks combined with 8 weeks forms the mid phase, and 12 weeks together with the 16 weeks forms the late phase. At each time point, we collected oviductal epithelial cells from the whole oviduct. For that, we straightened the oviduct and we milked, so to say, the oviduct to collect the cells. Then RNA was extracted from the cells and we did reverse transcription, after which we could finally perform qPCR to study the expression of marker genes for oxidative stress, endoplasmic reticulum or ER, and mitochondrial stress, and inflammation. So let us then have a look at the results. The difference in weight gain between the high-fat, high-sugar and the control group was already significant from 1 week onwards. On the right of this slide, you can see the difference between a control mouse and a high-fat, high-sugar mouse at the time point of 16 weeks. And you can clearly see the difference in the adipose tissue between the control mouse and the high-fat, high-sugar mouse at the time point of 16 weeks on the diet. So what happens at the gene expression level in the oviductal epithelial cells? In the acute phase, the acute responses to the high-fat, high-sugar diet indicated an increase in oxidative stress and in endoplasmic or ER stress, which was indicated by a significant upregulation of PRDX3 expression, which is a mitochondrial antioxidant, and of BIP expression, which is an ER chaperone. And this was together with a tendency for higher NRF2 expression. And NRF2 is a transcription factor that regulates the expression of antioxidant proteins, such as mitochondrial SOD2. And this was indeed followed by a significant upregulation of SOD2 in the early phase, together with a tendency for higher PRDX1 expression. And here in this early phase, the ER stress was temporarily normalized. When we did an extended exposure to the high-fat, high-sugar diet for 4 weeks till 8 weeks, there was again a second wave of the NRF2 SOD2 antioxidant response, together with significant upregulation of the ER stress, so a significant upregulation of the BIP expression. These mid-phase responses remained obvious during the late phase and were there accompanied by a significantly higher expression of the interleukin-1 beta, so an inflammatory marker, together with a significant upregulation of PRDX6. And this is no coincidence, since PRDX6 regulates the TNF-induced apoptosis through interleukin-1 beta production. In this slide, we can see the graphs with the expression levels of all the genes that were significantly affected by the high-fat, high-sugar diet. And as you can see, all the changes that I mentioned in the previous slide were always an upregulation of the expression of the affected genes due to the high-fat, high-sugar diet. So to summarize these results, we can say that exposure to a high-fat, high-sugar diet results in an acute oxidative stress in the oviductal epithelial cells, evident already after 3 days. And this initiates a cascade of transcriptomic changes that appears to control mitochondrial ROS production and ER stress. However, this could not avoid ultimate signs of inflammation in the late stage of long-term high-fat, high-sugar feeding. So to conclude, these results, based on transcriptomic changes only, suggest that consuming a high-fat, high-sugar diet, even for a short period of time, might compromise the oviductal microenvironment and may thus affect fertilization and/or early embryo development. To end with, I would like to thank you all for your attention, and I would like to thank all my colleagues at the Gamete Research Center who helped me with my experiments. If you have any questions, I am happy to answer them.